All right, we're going to be looking at exponential functions again, but today we're going to start looking at the graphs of exponential functions. So an exponential equation is an equation where you have y equals b to the x. B is going to be greater than 0, so it'll be a positive number, and then x is your exponent. Okay, so the reason this one is called an exponential equation is because your exponent, x, is your variable, x, is the exponent. Okay, so that's how you can tell if you have an exponential equation, is if your variable is the exponent. Okay, so we're going to look at a basic one, y equals 2 to the x. So since we don't know what this looks like, we're going to start with a table. Plug in some values and see if we can figure out what kind of shape these exponential functions are. Okay, so we're going to start with -3 for an x. So this would be y equals 2 to the -3rd power. All right, well, last week we talked about how you can do the reciprocal of a negative exponent. So this would be 1 over 2 cubed, which would be 1/8. So then we'll do the same thing for an exponent of -2, 1 over 2 squared, so 1/4. Now 2 to the -1st power, so 1 over 2 to the 1st, so that's 1/2. And then 2 to the 0 power will be 1, and notice this pattern. So as we're increasing our exponent, you can see that my value is getting multiplied by 2. So then the next one, 2 to the 1st, that would be 2. So again, you're multiplying by 2. So 1 times 2 is 2. And then if we have an exponent of 2, that'll be 4. So again, 2 times 2 becomes 4, and then 8. Okay, so at -3, we have 1/8, so it's just a little bit above 0. At -2, you have 1/4, again, just a little bit above 0. -1 is a half. 0 is 1. 1 is 2. 2 is 4. And 3 is 8. Okay, so you can see once we get past 0, this function really increases quite rapidly. Okay, so there's your graph of y equals 2 to the x. Okay, now you could also do that on your calculator, but I wanted to definitely go through and show you that table and that table of values and how those are related to one another. Okay, so the second example is, well, what if we have 1/2 to the x power? Okay, so let's plug in values. So we're going to have 1/2 to the -3rd power. So a negative exponent, do the reciprocal. So this actually becomes 2 cubed, which is 8. Okay, then we have 1/2 to the -2 power. So again, do the reciprocal, and that will be 4. And then 1/2 to the -1st, do the reciprocal, 2. So you can see what's happening here. So as my exponent increases, I'm multiplying by 1/2. Okay, this 1/2, that's called the growth factor. Okay, that's going to be important to us. So I want to throw out that term right now. So again, you can predict. So if I'm multiplying by 1/2, I've gone 8, 4, 2. Half of 2 is going to be 1. But again, you can put that in as an exponent. That exponent is 0. Anything to the 0 power is 1. And then if you put in a value of 1 for your exponent, you're going to get 1/2. Again, we just keep multiplying by 1/2 each time. So this is going to be 1/4, and this will be 1/8. Okay, so notice multiplying by 1/2 then takes you to the next value as you're increasing your exponent. Okay, so at -3, label my axes. At -3, you are at 8. At -2 is 4. -1 is 2. 0 is 1. 1 is 1/2. 2 is a fourth. 3 is an eighth. Okay, so this time, oops, my exponential curve looks like this. Okay, so you can notice the one previously was increasing as we look at it from left to right. And then this one is decreasing as you look left to right. Okay, so based on the graphs and the behavior you saw in the first two examples, state the domain and the range for an exponential function of the form y equals b to the x. Okay, well, domain is your x values. And if you look at the kind of x's that we chose positive x's, negative x's, 0. So really, it looks like you can choose anything you want. So that means the domain is going to be all real numbers. Now, if you like interval notation, you can say -infinity to positive infinity, or you can just use the real number symbol. Okay. For your range, if you look at both of the y columns and look at your graph, you can see that all of them are above 0. Now, your graph comes very close to 0. Okay, we had those 1/2, 1/4, 1/8, but they're still positive. They're still above 0. So that tells you your range is going to be real numbers greater than 0, or if you want to use interval notation, it's 0 to positive infinity. Are exponential functions 1 to 1? How can you tell? Okay, 1 to 1 means that for every x there's exactly one y, and for every y there's exactly one x. Okay, so basically is if they pass the vertical test and the horizontal line test, then they are 1 to 1 functions. Okay, now we haven't talked about that a lot. But these are yes. Okay, exponential functions are 1 to 1. And what does that tell you about their inverses? It means that exponential functions do have inverses. So remember when we were talking about inverses, how on some graphs we had to limit the domain, because if we reflected the whole figure over the y equals x line, they were no longer a function. Okay, so we only looked at half of a parabola. So parabolas, quadratics, are not 1 to 1. Okay, so in order for them to have an inverse, we had to restrict that domain. Okay, with exponential functions, you don't need to do that. Okay, all right, so now we're going to look at another one. Look at y equals 7 times x, or 3 to the x power. Determine the y-intercept of this function algebraically. All right, so y-intercept, if you remember to find a y-intercept, you let x be equal to 0, and then you solve for y. Okay, and that's how you find your x-intercept, or your y-intercept. Okay, so y equals 7. We're going to put 0 in for the x. So y equals 3 to the 0 is 1, and y equals 7. So 7 is your y-intercept. Does the exponential function increase or decrease? Well, we have 3 that's been taken to that exponent. So if you go back to the previous examples, we were increasing when that b was 2, and we were decreasing when that b, that growth factor, was 1/2. Okay, so if you're using that as a comparison, 3 is the growth factor in this example. So if you go with what we saw before, you're probably thinking it's going to increase. Okay, it's a number greater than 1. It's going to increase, and you are correct. It will increase. Create a rough sketch of the function, labeling its y-intercept. Okay, so let's just try to do a couple of points. So we put in 0 for the x, and we got 7. Okay, if we put in a 1, if we put a 1 in for that x, y equals 7 times 3 to the first power, so that's going to be 3 times 7 is 21. So at 1 is 21. What happens at negative 1? Well, at negative 1, we would get 7 times 1/3, or 7/3, which then equals 2 1/3. Okay, so at negative 1, we're still positive at 2 1/3. Now we're just going to do a very quick sketch. We're going to take a minute, look at it on your calculator, so you can graph it on your calculator to see the same thing. So 0 is at 7, so we're going to call this 7. Okay, and then at 1, 2, 3, we're at 21. So I'm just going to estimate that would be about 14. That would be about 21. So at 1, you're at 21. At negative 1, you are at 2.5. So negative 1, you're at 2.5. So we're going to estimate about right there. Okay. And then I know that's only 3 points, but again, you've already seen the shape of an exponential, so it's going to follow that pattern. Okay, exercise 6. Consider the function y equals 1/3 to the x plus 4. How does this function's graph compare to that of y equals 1/3 to the x? And what does adding 4 do to a function's graph? Okay, well, with our previous experiences with functions, you might say this 4 is going to be some type of a shift. And if you said the 4 is a vertical shift, you are correct. Okay, so determine the graph's y-intercept. So we're going to do the same thing. If we want to find the y-intercept, you're going to let x be equal to 0, and then you're going to solve. So this one, y equals 1/3 to the 0 power plus 4. So this, anything to the 0 is 1, plus 4 is 5. So 5 is your y-intercept. Okay, create a rough sketch labeling the y-intercept. Okay, so let's do a couple of points here again. So x and y. So if x is 0, we know y is 5. Let's see what 1 is. So we would go y equals 1/3 to the first plus 4. Okay, so that would be 1/3 to the first. That's just 1/3. So this is 4 1/3. So 1 is 4 1/3. Let's see what happens at negative 1. So y equals 1/3 to the negative first power plus 4. All right, so do your reciprocal of 1/3. So that's going to be 3 plus 4 is going to be 7. So at negative 1, you're at 7. So let's just go 5, 10, 15. We're going to go 1, 2. Okay, so I'm counting. I'm labeling my axes differently on my y and my x. But as long as you just label and say what you're doing, that's fine. So 1 is going to be at 4 1/3. So just a little bit lower. At negative 1, you're at 7. Well, almost looks like it's a straight line. So maybe let's do another number. How about a negative 2? So y equals 1/3 to the negative 2 plus 4 power. So do the reciprocal. It's going to be 3 squared plus 4. So that's going to be 9 plus 4 is 13. So at negative 2, we're at 13. So that jumps quite a bit. Okay, so we have